Now let's get into the nanostructures which systematically interact with light. The first case I would like to introduce is photonic crystal. Photonic crystal is periodic arrangement of dielectric objects. Lattice constants comparable to the wavelength of light in the material. We have a variety of natural photonic crystal from morpho butterfly wing scale, beetles' back shells, peacock features, some tropical fishes' scales, and this sea mouse's hair. As shown in the right figure, sea mouse hair have iridescence property, which means the color is different when shed light from off normal direction. It was 1987 that the first artificial photonic crystal had been suggested by Yablonovich and John by using face-centered cubic superlattice which exhibits complete photonic band gap. Basically, photonic crystal is like semiconductors for light. According to the theory of photonic crystal, the use of strong index contrast, and the developments of nanofabrication technologies, which leads to entirely new sets of phenomena. Recently, new conceptual framework in optics such as band structure concepts and coupled mode theory approach for photon transport. In photonic crystal, wave vector determines the phase between nearest neighbor unit cells. For example, in two-dimensional photonic crystals with unit constant A, we can think of two different symmetry points. The first one is x, which corresponds to the reciprocal wave vector at pi over a and 0. Thus, nearest neighbor unit cell along the x direction is 180 degree out of phase. The second one is m, which corresponds to the pi over a and pi over a. Thus, nearest neighbor unit cell along the diagonal direction is 180 degree out of phase. Using some defects, it is possible to modify the photonic properties of photonic crystal. For example, in this two-dimensional photonic crystal, we can apply air defect or dielectric defect inside the crystal. Around the introduced defects, electromagnetic field is concentrated and not diffused into near the defects. This means that the light can't propagate from the defects and strongly localized around the defects. What if you can align the defects in a line shape? In others, it is possible to artificially arrange and align the defects inside the two-dimensional or three-dimensional photonic crystals. Then, the light inside the defects line can move along the linear defects path, which effectively works as a guide. And the light inside the linear defects can exhibit guided modes as shown in the middle figure. As shown in the right figure, computational electromagnetics such as finite difference time domain method clearly shows that the guided mode can form inside the defects line. This means that we can construct an optical path which works as circuit just like a metal circuit in microelectronics. Then what is the main difference between the conventional waveguide such as silicon on insulator waveguide and photonic crystal-based waveguide? As shown in this figure, the conventional waveguide depends on the high refractive index materials to confine the light inside the waveguide materials. In contrast, it is not necessary to use high refractive index. Instead, it is possible to use low refractive materials with designated periodicity and defects positions. Due to this property, photonic crystal waveguide can be applied to fabricate sharply bent optical path as shown in the right simulation picture. In addition, it is possible to construct micro-add/drop filter using the defect-associated photonic crystals. As shown in the rightmost simulation pictures, two resonant modes with even and odd symmetry can work as add/drop filter. By controlling symmetry, periodicities, and refractive indices, we can fabricate a variety of photonic crystals. Using these crystals, we can apply for various areas including enhanced nonlinear optical devices, optical filter, highly dispersive element, super prism, transformative optics, and metamaterials. Photonic crystals have unique photonic band gap, which makes the photonic crystals as a good optical filter. In addition, we can apply adaptive or transformative lattice such as spatially variant lattice to guide the light around the sharp corner. It is also possible to derive nonlinear optical properties in linear optical materials in an artificial manner. For lasing materials, 1D photonic crystal can work for the perfect nanoscale mirror to amplify the coherent light. Photonic crystals for the application for metamaterials have obtained increasing research interest in recent years. We will explore in detail in the Lecture 5. Using three-dimensional photonic crystal, it is possible to fabricate superlens as shown in the upper left figure. Using honeycomb structure with alternatively stacking order, the photonic crystal disperse the incident light with wide angle. In addition, this photonic crystal can also work as super prism, which make conventional diffraction into non-conventional diffraction. Wide incident light is diffracted by the photonic crystal. Very slightly different wavelength suffers greatly different diffraction by enhanced light propagation by the designated photonic crystal, which distinctively separate the two light wavelengths. For three-dimensional photonic crystals, complete band gap is observed in both air spheres and dielectric spheres. However, refractive index ratio needs to exceed 2 in order for band gap to open. Optimal structure consists of connected dielectric and air networks. Typically, three-dimensional photonic crystal is harder to be fabricated than two-dimensional photonic crystal. They require complicated nano-patterning process along with deposition and etching. Instead of the conventional nano-patterning approach, some strategy can be done using bottom-up approach such as colloidal particles assembly as shown in this picture. As shown in the right plots, the fabricate three-dimensional photonic crystals can work as a complete photonic band gap. In plane 2D photonic band gap provides complete in-plane confinement. Out-of-plane confinement provided by high-index guiding. It is easy to fabricate. In the photonic crystal slabs, radiation modes above the light line. Losslessly guided modes below the light line. Incomplete band gap in the guided mode spectrum. The photonic crystal slab successfully works as waveguides as shown in this figure. For example, silicon can be sandwiched between photonic crystal of silicon oxide layers. For relatively lower frequency, this structure can form slab modes for wide range of wave vector. As shown in the right simulation pictures, the waveguide can be done in the slab modes regions, while the guiding quality is not good for the radiation modes as shown in the upper simulation results. Photonic crystal can be applied to optical fiber. Typical optical fiber is composed of inner core and outer clad. The inner core is the critical part of the fiber as an optical guide, making the complete inner reflection. Photonic crystal fibers guide light by corralling it within a periodic array of microscopic air holes that run along the entire fiber length. For typical optical fiber, the core is silicon with germanium doping. The cladding is silica. The core diameter is about 5 to 8 micrometers. And the outer diameter of the cladding is about 100 micrometers. However, the conventional optical fiber has some shortcomings. The major problem is propagation loss. This is due mainly to Rayleigh scattering, in which random localized variation of the molecular positions in glass creates random inhomogeneities in refractive index. Another factor is infrared absorption from vibrational transitions. At absolute minimum at 1.55 micrometers, the loss is 0.16 decibel per kilometers, which indicates 3.6% signal loss per kilometers. This means that fiber optical amplifier is necessary for long-distance communication. To overcome the problems of optical fibers, photonic crystal can be used for waveguide. As shown in the left figure, photonic crystal fiber can be prepared using macroscopic preform with the designated periodicity. And the preform fiber is placed in the furnace to soften the silica, and the softened fiber can be narrowed down and cooled to form thin fibers. Photonic crystal fiber can be prepared in either dielectric core type or air core type as shown in the right optical microscope image. The cladding in the photonic crystal fiber works as a mode sieve. The lower modes cannot escape as the wire mesh are too narrow. The higher order modes can leak through the narrow strip. Increasing the relative size of the diameters of holes with respect to the pitch leads to the trapping of higher modes. Single mode behavior occurs when the ratio between the hole diameter and pitch is smaller than 0.4. Using air core photonic crystal band gap fibers, 13 decibels per kilometer propagation loss can occur. The loss is primarily due to the coupling of core modes to surface modes, and likely can be further reduced significantly in newer design.